Hey everyone, this is Daniel for Rock the JVM. This video is a conference talk that I held at Rheinwerk Konference für Kotlin 2024, or KKON 2024, a couple of weeks ago, and I talked about the differences between Kotlin and Scala. The title of the conference talk was What Kotlin Can Graciously Steal from Scala. Obviously, that was a Kotlin conference, but many of you here on the Rock the JVM channel are Scala fans, and Scala is still by far my preferred programming language, so you can give it a slightly different title in the form of something like what Scala graciously has over Kotlin. This is essentially a Scala and Kotlin language comparison, not just in terms of language features, but rather in terms of mental models and the kind of thinking that Scala still enables you to do that many programming languages, including Kotlin, still do not. Now, in this video, I'm going to talk mostly on the original slides of the conference, but you're going to get an even better version because I'm on my YouTube channel and I can do whatever I want. So I will stretch this conference talk with some coding examples as well because I want to illustrate some points better. So you're going to get an even better version of the conference talk. Okay, so without further ado, let's talk about how Kotlin was inspired by Scala. So more than 10 years ago when Kotlin came out, the creators of the Kotlin language were essentially looking for a programming language that satisfied their needs. And at the time, Scala was the only language that could satisfy those needs. Now, the problem was that at the time, Scala compiled quite slowly, so they wanted to create a new programming language to get the best features of Scala and with the fast compilation speed of Java. So they wanted to get the flexibility and the expressiveness of the Scala language, but the speed of compilation of Java. So this informed some important features in the Kotlin language, which is the concise syntax that is heavily inspired by Scala, type inference of the compiler, the type safety of the Kotlin type system, which is better than Java's, and this was inspired by Scala as well, the difference between mutable and immutable collections in the standard library, some OOP principles that are slightly loosened out so that you can enable some greater productivity without the need to follow some strict Gang of 4 patterns, first-class support for functional programming, which at the time only Java 8 could do with very minimal lambdas and minimal expression-oriented programming, records and destructuring, which Scala has pioneered for more than a decade, and string interpolation, which is a little bit more minor, but it's still very, very useful and enables great productivity. So if you take a look at this code, one section is in Kotlin and one section is in Scala. I'm going to give you a couple of seconds to figure out which is which. So at this point, I think you can tell which one is Kotlin and which one is Scala, but it's not really trivial to find out the differences because the structure of the language is so similar that the languages look almost identical with minimal code examples. So this particular code example was taken from Wikipedia, and I wrote the examples both in Kotlin and in Scala. The example on the left is in Scala, and the example on the right is in Kotlin, but you can tell the similarity between these two languages. They look almost identical. Now, over the rest of this video, I'm going to talk about the differences between the languages, not just in terms of language features and the structure of the language itself, but in terms of mental models and the kind of productivity that each has enabled us to do. So I'm going to talk about pattern matching first as one of the warm-up examples that Kotlin can do better in terms of destructuring. So Kotlin currently has when clauses, which is good for type tests and flow typing because on the branches you can essentially validate that a variable conforms to a certain type. And it's probably inspired by Scala pattern matching because it looks so similar. I say probably because I can't know for sure, but the expressions look too similar. So if you take a look at these code examples, one is in Scala and one is in Kotlin. I have a sealed trait with a couple of cases. One is a circle and one is a rectangle with different data inside of them. If you take a look at the pattern match in the Scala code example, so here when you do shape match and you have a case circle and case rectangle and you return a different expression depending on the types and on the structure, Kotlin looks very similar. It has a when clause, and when you have when shape is circle and is rectangle, then you can take the data and use the methods of that particular type in the expression that you want to return. Now, at the time of this recording, Scala is still far more powerful than Kotlin because not only can it destructure the data right here, but it allows you to decide and write your own destructuring logic, which Kotlin obviously does not allow us to do. So Kotlin can steal some structure decomposition and maybe, just maybe, an advanced API to do your own destructuring patterns. The benefits for Kotlin productivity would be some better, quicker destructuring and cleaner code because you don't have to refer to the same variable over and over again. And it's such a better fit for functional programming rather than just a switch on steroids or just a bunch of instance of tests in the same expression. So Kotlin currently looks something like this when you have a when clause and you have some type tests, but it can become more like this, where you could destructure the variables in question into their respective structures. And this could very easily be Kotlin. Now, I understand that pattern matching is very hard to implement, and destructuring over a variable kinds of structures, especially with nested data structures, is hard. And I understand why such a feature would probably take a little while to arrive in the Kotlin language, if at all. But it would enable greater productivity and some cleaner code because it's quite clear that once you conform to a certain structure, you can extract the particular data and also the methods and the behaviors of those particular types. Now, I use pattern matching as a warm-up example because where Scala truly shines is in contextual abstractions, which is the ability to grant some special functionality under some context and not others. And this can become a topic on its own and a conference on its own. But I'm going to keep it short just in terms of this contextual abstractions, in terms of the mental models of these languages. So originally, Scala 2 had the implicit keyword, which was overloaded with meaning. So you had implicit classes as automatic wrappers, giving you access to essentially new methods to existing types, so extension methods. Then you had implicit arguments to methods as some context requirements, along with implicit values as proof of that context. And then we had implicit methods as automatic conversions or proof generators. So the ability to synthesize instances that could then be passed automatically as implicit values. So the implicit keyword was filled with meaning. Then you had in Scala 3 replace the implicit keyword with new keywords and with new situations with their respective meaning in their respective fields. So we had the implicit class now replaced with the extension keyword, which is far clearer. Then we have implicit values and methods with given instances, and then the implicit arguments with using clauses. So now it's very clear which contextual abstraction should be used when, instead of relying on the old implicit keyword. Now for us, this is both a source of happiness and also a source of confusion, because on the one hand, we get elevated abstraction power, which allows us to focus on the higher level thinking, but also it's a source of confusion because unless you're really careful, you can get to some very gnarly situations where it's hard to trace where contexts came from, or code bases that are hard to read and understand, especially for beginners, which also gives Scala this apparent complexity. So Kotlin wanted to avoid some of that and only developed extension methods as first-class syntax, which Scala 3 also has, and it also developed context receivers, which at the moment of this recording, they're experimental, and they will be deprecated in favor of context parameters. And I'm going to give some demonstrations in the code a little bit later. Now, let me give you a code example of where contextual abstractions can be useful. So let's take a look at this little piece of code. So let me assume that I'm working on some sort of jobs board, and I have a bunch of pieces of code written from different places. For example, some piece of code from a library that I want to use, like SLF4J or something like that. So an interface that is called a logger. I'm just simplifying the interface here. Then we have a piece of code that we've written internally, like a little small framework. Then I have a JSON scope with an extension method that gives me the ability to serialize an item to JSON because I'm using an HTTP server, and JSONs are pretty much first-class citizens of any web application. And then the business logic is described by the interface jobs with a bunch of functionality like the ability to find a job by its ID or show job details or things of that sort. So this is in Kotlin. And in terms of the implementation of these layers, we have values that conform to these types. So maybe anonymous classes or real classes that you can instantiate multiple times and things of that sort. Now, if you want to give some functionality in a particular context, we have context parameters, or context receivers, the way they used to be called. So only if you have a logger instance can you build a class LiveJobs with a particular implementation of find by ID, or in the context of a particular JSON scope and in the context of a logger. So if you can pass them in a higher level structure, you have the ability to call the method print as JSON, which takes a bunch of things as a list of A, and it returns a string, maybe a serialized JSON list. So the context parameters here will help Kotlin grant you the capability of either building the LiveJobs instance or using the print as job functionality. And the way that you would use that would be to say with job JSON scope, with console logger, and only inside that scope can you use the print as JSON functionality or instantiate the LiveJobs instance. Now, in Scala, you would have a very similar thing where we describe interfaces as traits. It's just a keyword difference. And the scope is still described as a trait in which we have the extension method with the extension keyword. And the business logic is obviously described as another trait, and we can implement them as regular values. Except in Scala, with contextual abstractions, we can implement them as given instances. So given instances are essentially glorified variables that the compiler can pass automatically wherever it uses a using clause of that particular type. So in our case, the layer of the library, the console logger, is a given value where we override the info method. The job JSON scope is, again, a JSON scope instance where we override the toJSON extension method, and so on and so forth. And the class LiveJobs, look at this particular definition. The class LiveJobs can only be instantiated if you are able to grant the presence of a logger instance wherever the LiveJobs needs to be instantiated. So in the scope where the LiveJobs needs to be instantiated, you must have a logger given instance, which the compiler will pass automatically. And likewise, with the print as JSON, we say we are using JSON scope A and logger. This is a replacement for the context parameters in Kotlin. Now, the advantage in Scala is that we don't have to pass them explicitly because the compiler finds them automatically and passes them automatically as well. And if it cannot find them, then the code will simply not compile, thereby granting the correctness of the description of print as JSON. So the signature makes the compiler not compile the code unless you're able to give the JSON scope and logger in that particular place. So again, in terms of comparison, Scala versus Kotlin, we have interfaces and traits with slightly different language structures, especially in the extension method kind of thing. And in terms of the implementations, we have values or variables in Kotlin, and in Scala we have given instances which the compiler can pass automatically wherever it uses the using clause. So instead of a context here, we have the using clause in Scala, and instead of context with multiple variables, we have the using clause with multiple types in Scala. So in this case, Kotlin and Scala are quite similar, except that in the usage side, we need to pass them explicitly in Kotlin, and in Scala, the compiler passes them automatically, or it does not compile the code at all. Now, one area where Kotlin lags behind Scala is the ability to synthesize new given instances based on existing ones, besides the need to pass the context values explicitly. So let me show you something. I have my dev environment here. On the left-hand side, I have Kotlin, and on the right-hand side, I have Scala. I'm going to write some Scala code first, and then I'm going to write the Kotlin equivalent of that. Now, I'm going to share a quite simple example so that we have the space here to understand in just a few lines of code. So let me write a simple method to combine all items of a list of integers. So I'm going to say combine all int, like an int with a list of int. And this returns an int as ints reduce. And I'm going to have the lambda that sums two items. So ints reduce underscore plus underscore. Underscore plus underscore is just a shorthand for a lambda that takes two arguments and just sums them together. Likewise, I can have combine all string, for example, string with strings as a list of string, and I'm going to return a string, and I'm going to have strings reduce underscore plus underscore, and the implementation can be the same, but the effect is different. So in this case, we have concatenation, and in the first case, we have addition. And we can sum up many different kinds of things depending on what the plus operator is implemented for that particular type. Now, if you wanted to abstract away this kind of concept, the concept of addition, you would describe that by a trait. I'm just going to call this combiner with the type parameter a, and I'm going to have a combine method. So combine with two values, a and b of type a, and we would return a third item of type a. Now, with this trait combiner, I am going to define a higher level combining method that takes a list of any kind as long as we have a combiner in scope. So I'm going to have, let's call this combine all. With the type parameter a, I'm going to have some items as a list of a, and I'm going to pass my combiner as a second argument. So I'm going to have combiner as combiner a. Now, Kotlin doesn't have multiple parameter lists, but it can I can simply pass this as the second argument, and I'm just going to return a value of type a at the end, and I can say items reduce, and I'm going to say combiner combine instead of the plus operator. So instead of the plus operator, the combiner decides how two items of the same type can combine. So, for example, in main, I'm going to define some values. For example, I'm going to say val int combiner as combiner a, so new combiner int. With override combine, I'm going to say a plus b, and I'm going to have val string combiner as new combiner string, and I'm going to have override the same thing, a plus b. So the int combiner and string combiner are abstracted away into this new type, and in main, obviously, I can say, for example, print line combine all, so combine all with a list of 1, 2, 3, 4, 1, 2, 3, 4, and new combiner of int, which I've already defined, so int combiner. And that should give me back the sum of all the numbers. Now I need to pass parameters correctly here. And if I run this application, I am going to obtain the number 10, which is the sum of all these numbers. Now, unlike Kotlin, I can organize my code such that this int combiner and string combiner, or whatever combiner of my required type, can be passed automatically or implicitly. So instead of this int combiner, I'm going to say given. So given int combiner, and this is going to be a combiner int. Or I can say combiner int with, and I can compact my code a little bit. And similar for string, so given string combiner as combiner string with. And in combine all, I'm going to have my using clause. So using combiner as combiner a, and I can cut this all together, and the compiler will pass that automatically for me. So I'm going to say combine all with a list of any kind, and as long as I have a combiner of that particular type in scope, the compiler can inject that automatically, and obviously the code will compile and it will run, and this will give me back number 10. And I can say print line combine all with a list of strings, for example, Scala, and then is, and then cool. And likewise, this expression will compile because I have combiner string in scope. So we have this concatenation. So the int combiner and string combiner can be placed pretty much anywhere. So you can simply say combine all, and as long as you have that thing in scope, the code will compile and it will do what you expect. And you can also import these values automatically and have the compiler pass them as well. Likewise, Kotlin has this capability, but you have to give the context explicitly. So if I wanted to simulate this in Kotlin, I would paste these methods. I would have fun instead of def, and I would have int.reduce, and this would be a list with angular brackets instead of square brackets, because why not? And I'm going to have ints reduce ab, arrow a plus b, and likewise for strings. So fun, combine all strings, list of string with angular brackets, and I would have strings reduce with the same kind of lambda, and I would have the same kind of code. Now, instead of a trait, I would have an interface. So an interface, we have combiner of a, and I would have a fun combined with two values of type a, returning a third. And this int combiner and string combiner, I would have that as values. So I'm going to have, let's call this int combiner as object, which extends combiner int, and I'm going to have my override combine. I'm going to have return A plus B. Likewise, I'm going to have a val string combiner, so string combiner as an object that extends combiner string, and I'm going to have my override combine, override fun combine, and I'm going to have return A plus B. So pretty much the same thing. Now, with my little API, I would have my context. So I'm going to say context combiner A. I would have fun A combine all. I'm going to have items as a list of A, and I'm going to have my A as the result. And I'm going to have items reduce, and I'm going to have AB. I'm going to have combine A and B, because I have access to the combine method given the fact that I'm inside the context of combiner A. So I can simply use the methods of combiner A as my little functionality. And in my main, I can use my context. So I'm going to say with int combiner. I'm going to say print line combine all with a list of 1, 2, 3, 4, and combine all is available in the presence of the int combiner, and I cannot do that with the string combiner. So if I do a print line with combine all, as I did in Scala, so I'm going to say list of, I'm going to say Kotlin is cool, so that we don't spell anathema. And here in this case, the code doesn't compile because I'm not in the presence of the string combiner. I can only do that in the appropriate context. So I'm going to say with string combiner, I can only then combine all of the list of strings, and I can separate my contexts by passing them explicitly. Obviously, this thing is a little bit clunkier because you have to be careful which context gives you access to which code, and it's a lot more verbose and more explicit, whereas in Scala, we have them passed automatically. That's not necessarily what I wanted to show here. Here in Scala, we can synthesize new given values based on existing ones. So for example, if I have access to an int combiner or a combiner A, I can also synthesize combiners for options A or for lists of A or things of that sort. So I can write something like given option combiner A, with using combiner as combiner A. So in the case that I do have access to a combiner A, I'm going to make the compiler automatically synthesize, if needed, a combiner, so combiner of option A, for any type. So as long as I have combiner A, I can generate a combiner option A with my override combine. And in this case, it takes two options and returns a third. And I can use pattern match. So A, B match, and I'm going to say case sum with the value A and sum with the value B. I'm going to return a sum with combiner combine value A and the value B. Case sum with the value A and none, I'm just going to return sum VA. Likewise for the reverse, so in case none and sum VB, I'm going to return sum VB. And in case whatever, I'm just going to return none. Now in this case, I can combine lists of options int. So for example, I can say list of option 1 and then a none, and maybe option 2 and maybe another none, and maybe sum 3, and maybe another sum 4, whatever. And this thing compiles because as long as I have a combiner of int, I can generate, so I can make the compiler generate automatically a combiner of option int. So if I cut out the int combiner, not only will the first thing not compile, but the third thing will not compile either, because I don't have, or the compiler doesn't have the capability of generating the correct implicit value to pass here automatically. So the ability to synthesize new values, new contexts based on existing ones is what grants Scala enormous expression capability, and the ability to generate what is called a type class. This thing is called a type class, and the correct mathematical term for that is called a semigroup. In Kotlin, we also have the concept of type classes, or we can generate something like that, something like type classes. And we have an entire video and article on type classes in Kotlin, but it's a little bit more clunky. And we also don't have the ability to generate new type class instances, which is what these given values are, for new types based on existing ones. So back to the original conference talk. So Kotlin is doing some things right. It's using context parameters as implicit arguments, and only within those contexts can you access some special functionality, and outside that context you cannot. And you can also access the context value with context parameters in the future instantiation of this feature. And what Kotlin can quote-unquote steal from Scala is this context value generation, which Scala does beautifully. For less boilerplate and automatic synthesis of new context instances, and the ability for the compiler to pass those things automatically. Now, honestly, I doubt that Kotlin will take this from Scala, and this will continue to give Scala an advantage in abstraction power over Kotlin, in my estimation. Now, the next thing that I wanted to talk about is higher kind of types. Kotlin currently has Java-style wildcards, but no type constructors, which is the ability to express the type that takes generic type arguments. So the type itself, for example, list, or option, or either, and things of that sort. Let me give an example. So I'm going to run another demonstration here. I'm going to start with Scala. So currently, Scala has what is called higher kind of types. Higher kind of types are generic type parameters which are themselves generic. So let me give some examples. So higher kinded types here. And I'm going to give an example. So if you imagine the ability to map over something, you can imagine mapping over a list, for example. So modified list as list 123.map_+1. So the ability to map over a list returns a new list. A modified option, let's say, is, for example, an option 43 or 42, map_+1. So in this case, mapping is not iterating, but it's transforming a container into a container of potentially a different type, but with this function applied to the element inside. Likewise, you can map over a try or a future or things of that sort. I'm going to give one more example. So modified try as, say, try with a 45.map_+1. You get the idea. Okay. Now, try needs to be imported, so I'm going to import Scala util try, and you can map over many, many, many kinds of things, so over trees, over futures, over effects, over many different kinds of things. Now, the ability to map over something, I'm going to describe by a trait. I'm going to call this mappable. And I'm going to take a type parameter m, which is itself generic. So this is called a higher kind of type. It takes what is called a type constructor as an argument. A type constructor is like list, or option, or try itself, without passing the generic type parameter to that. So list, option, try are type constructors they can pass instead of this m here. And this mappable can take a function like a map that takes two real type parameters, a and b, so these are not generic. And you can take a container like an ma, for example, a list int, for example, and a function from a to b, for example, a function from int to string, and it gives you another container, mb, which is a list of string in this case. So you can take a list, then two type parameters, for example, int and string, and you take a list of int, a function from int to string, and you obtain a list of strings. So this is what these MAB signify. Now, as we did before, we can instantiate this mappable not necessarily as values, but as givens. So I can say given, let's call this list mappable, as a mappable with list. So notice that I'm not passing list int, list string, whatever. I'm passing the list type constructor itself, so mappable list, with override map, and I can say ma map f. So I'm mapping over a list. I can say given option, given option mappable as mappable option with a similar kind of thing. Override, I'm going to say ma map f. So you can map over options. You can say given, let's say try mappable as mappable try with override, and I'm going to say ma map f. Okay, so you can have these mappable concepts instantiated for list, option, try, future, IO, and whatever else you want to use this for. And then you can create higher level abstractions. For example, the ability to multiply or convert or transform a container, let's call this multiply, that takes a type parameter m, which is itself generic. So this is a type constructor here. I'm going to say a container as an m int. So container is an m int. And I'm going to say using mappable as a mappable m. And I'm going to say mappable map over container. In the transformation function, I can say underscore times 10. And this multiply thing works for list, option, and try because I have the instance mappable of their respective type constructors in scope. So for example, I can say print line multiply with list 1, 2, 3. And this thing compiles because I have a given mappable of list in scope. So the mappable, mappable list is passed here. Mappable list or whatever, list mappable. This thing is being passed by the compiler automatically. I don't have to pass it myself. The compiler does that automatically, and same for option, try, and whatever else you want to use for your application. Now, you can also simplify and make this API a little bit more expressive, and I'm going to write that in a companion object of mappable, and I'm going to have an extension, so mappable. And I'm going to have an extension, so extension, considering the type m, which is itself generic, so a higher kind of type, AB. I'm going to have the container as an MA. So any container MA, for example, a list of int, will have access to a map method, which is an extension method, FA arrow B. As long as I have a mappable in scope, using mappable as a mappable m, and I'm going to say mappable map container f. Now, what does this do? It gives me the ability to map over something, even though that particular container m may not necessarily have the map defined in its type, but I'm going to grant it as an extension method, as long as I have this context and scope. So the context of mappable grants me the ability to map over a potential container, even if that container doesn't have that map method internally written. For example, in this case with multiply, I can simplify this API. I can say, let's call this multiply version 2 with a type parameter m, which is generic, so a higher kind of type. I'm going to say container as an m int. Okay. And I'm going to have an import. So an import mappable star. Okay. And I'm going to say using mappable m. I don't even need to name it here. I'm going to say using mappable m, and it gives me an m int at the end. And I'm going to say container.map underscore times 10, whatever container is. So the container can be an IO, it can be a tree, it can be a list, it can be anything. If I have the mappable m in scope, I am granted the map extension method for this container, whatever the container is. And I can simplify this further. In Scala, we have some compact syntax for that. We can say that m is a mappable. So this is called a context bound. So this using clause can be compacted away by saying m, quote unquote, is a mappable. And if it is a mappable, then it has access to the map method, whatever m is. So this thing can use multiply or multiply version 2. It works in the exact same way. Now, unfortunately, I cannot translate either of this code in Kotlin. The ability to do higher kind of types does not exist in Kotlin at all. So Kotlin has these Java-style wildcards, but Kotlin can take from Scala these generic types with generic type parameters themselves, which are called higher kind of types. Now, as far as I'm aware, the opinions inside the Kotlin community about higher kind of types are split, and Kotlin has decided not to take higher kind of types because they would apparently complicate the language. And it also does give a language this apparent complexity, but it also grants it enormous expression power. So the benefits to that would be elevated abstraction levels and some increased expressiveness, which allows you to focus on your business level without caring what kind of types you're working with, as long as you gave them the right context. And if you happen to combine contextual abstractions with higher kind of types in the style that I've showed you in the code, this is super powerful for code reductions and for mental burden reduction, because now you can focus on what you care about without caring about the correct types or with the correct context, as long as you created them in the first place. Another thing that I wanted to talk to you about is the ability to describe programs as values. Kotlin currently has suspend functions which describe code that may not run immediately when called. These are essentially descriptions of what code will be run if those suspend functions are invoked. And suspend functions are tightly integrated with the rest of Kotlin. This is great. So let me show you a layer in an application that I wrote in a long course that I have at Rock the JVM called the type level rite of passage. This was written in Scala with the cats effect and the type level libraries translated into Kotlin. So one of the core modules in this particular application was the module for authentication and authorization. This is the ability to log in, sign up, change password, and so on and so forth. All of these would, in Kotlin, be described with suspend functions. Suspend functions essentially describe effectful computations. And in the code snippet below with the live auth, this is the implementation of the auth module, where the invocation of, or the instantiation of this module is also effectful because it can spin up additional resources. So we have suspend functions all over the place. Okay, now let me show you the original code. So in the original Scala code that I wrote in the type level rite of passage and in the jobs board application that I deployed on Rock the JVM, I have the authentication module as a trait with a higher kind of type parameter f, which describes the kind of effect that will be returned. Maybe a list, maybe an option, maybe an IO, maybe something else. This is the higher level expression power that Scala grants you. And we have essentially the same functions with the same parameters, except we don't have the suspend keyword in front of them. Instead, we have f in the return type. Likewise, in the live auth implementation, or in the instantiation of the real implementation of the auth, we also have the apply method, which is essentially a smart constructor that is also effectful. So instead of the suspend keyword, we have the effect type f, which wraps pretty much every other value that we returned. Now, the important thing is the type class that this f needs to conform to. The type class essentially describes what it means for a computation to perform any sort of effect, like the ability to suspend, or the ability to cancel or error out, or the ability to execute synchronously, or any sort of ability, or multiple abilities, the ability to log something. Now, obviously, regarding syntax, you saw this before in the code where we had the colon mappable thing. So this is the context bound, which means that we pass implicitly, or the compiler passes automatically, a given mappable m in scope. Here we have a syncf and a logger f being passed automatically by the compiler. These implicit instances essentially describe what it means for that effect type f to be able to perform any sort of action in the real world, the ability to log or suspend or anything else. So essentially what you have is your own keywords. We don't have suspend, but we have much more. And we can grant these capabilities in the form of implicit type class instances that we pass automatically from the compiler. So as we mentioned earlier, Kotlin has suspend functions with the properties that we've described, but what Scala has over Kotlin is this ability to grant new powers to existing functions. So we can describe various kinds of effects or various kind of capabilities in the real world, and we can describe them as we see fit and pass them whenever the context requires them. So Kotlin could steal from Scala these sort of functions with powers, which are essentially configurable keywords, but I really doubt that Kotlin will take this in the language because it grants this sort of apparent complexity, although there are only a couple of principles to understanding this sort of thing. So with just a couple of ideas, you can make your code extraordinarily modular and composable. Here, what you see on the right-hand side of the slide is the core module of my type-level rite of passage application. This is where the entire application is spun up. We have jobs, users, tokens, emails, authentication, the credit card checkout, and all the external services that we use in the application. And we can build the entire functionality in the app with a single expression. And the modules can also take care of themselves and have their own capabilities that they require independently. So to sum up, Kotlin was super inspired by Scala to have this concisiveness and the expressiveness granted by the Scala structure and the Scala mental models with better compile times. Also, Scala caught up on those compile times with the recent addition of Scala 3. However, Scala still has an advantage over Kotlin in the number and kinds of ideas you can express, including pattern extractors, which can simplify your code, context derivation and synthesis, type classes, higher levels of abstractions, and programs as values with the prevalence of effect libraries like Cat's Effect and Zio, and much more. Scala also has type proofs and enforcers, or new types, so type-level programming, structural types, type class derivation, and not to speak of macros and metaprogramming, which blows up the kinds of libraries and tools that you can create with the Scala language. So Scala and Kotlin are amazing languages for their own purposes. This presentation is not to say that one is better and one is worse. There are obviously trade-offs to both. I personally prefer Scala because of the ideas that I can express in my code, and the code looks beautiful to me, not just functional and fast. So I just wanted to share some features that will allow you to think better and that you can use to grow yourself as a developer, regardless of which language you end up using. I hope you enjoyed this video. If you did, go ahead and click the like button for me and subscribe to the channel for more videos like this. If you have any questions about the conference talk or about this video, you can find me at Rock the JVM on all socials, and you can email me at daniel@rockthejvm.com. Until next time, folks, this is Daniel signing off.